We are making our way through circuits, and we have found how to figure out the current running through a single resistor system. However, we're pretty much never going to have a single resistor system, except we can take systems with many resistors and condense them down to one equivalent resistor. So we are and are not going to have single resistor systems. This is going to be a video about resistors in series and parallel. Okay. If we have a resistor and it looks like a straw, when I started doing resistors, I said you could think of resistors as being like straws for drinking milkshakes. If I do this and then I add another straw next to it, even if the other straw that I add is really thin, I am now going to get more milkshake drinking from these two straws together. For the same amount of effort, I'm going to get more milkshake than I did before. So by putting these straws next to each other, my total resistance must be going down. If I take a straw like this and then say, let me do the thing where I attach one straw to the end of the other to make it longer. In this case, it's going to take more effort than it did with just one straw, so my total resistance is going to have gone up. This thing is called a parallel arrangement, and this thing is called a series arrangement. And we can get to a point pretty quickly figuring out just how that resistance is going to go up or down. This is kind of the why of it, but let's do the how. When I'm connecting two resistors in series, I'm looking at this. Remember that resistance looks like a row times the length over an area. So if I take a resistor like this, and for this example, I'm going to make sure that these resistors have the same area. They don't have to, but it makes it a little easier to see the math. I take a resistor like this, and I take a resistor like this, and let's call this one a length L. And this one a length L. The total resistance that I have now I've got a row times, if this whole thing is one resistor, L1 plus L2 over A. And now I can split up a sum in the top of a fraction. I can say this is row L1 over A plus row L2 over A. This thing, row L1 over A, that's just my first resistance. This one's just my second resistance. So in series, for two resistors, I get just the sum of their resistances. If I had had a third here, if I had had a plus L3, then there would have been a plus row L3, plus row L3 over A, so I would have had a plus R3, however many resistors I've got. So in series, resistance adds. Now let's look at parallel. If I've got two resistors, and I'm going to make these the same length as each other. One resistor like this, and another one like this. Now I've already established that even though the second resistor is really small, it's still going to decrease the total resistance of my system, right? If I drink through two straws, it's going to give me more milkshake than if I drink through one. So the total resistance of a parallel arrangement is going to be lower than the individual resistance of any of the resistors that make it up. Meaning, if this is a 100 ohm resistor and this is a 1000 ohm resistor, my total resistance will be less than 1000 ohms and it'll be less than 100 ohms. But let's see what happens. My total resistance is going to be rho times L over, and now it's the areas that add up. Now I've got a problem because I can't split up what's going on in the bottom of a fraction. That doesn't work. What I can do is introduce this second concept of conductance. Conductance gets the letter G, and it has units of inverse ohms, or mhos. This is about as funny as the people who name things get, at least in the world of physics, because mho is just ohm spelled backwards. G is 1 over R. So if resistance is a measure of how well a resistor prevents current from moving through, conductance is a measure of how well it lets it through. Which means my G total, it's 1 over R. My G total looks like this. Now I can split up the sum in the top of this fraction, so that is A1 over rho L plus A2 over rho L. This first one, that's just G1. The second one, that's just G2. If I had another, I could add a G3. So my G total equals G1 plus G2 plus G3 plus whatever, which means it is my conductance that adds. In parallel. If I wanted to find what my total resistance was at the end of something like this, I would take my conductances, add those up, and then in the end, once I've got my G total, then say R total is 1 over G total. And that'll get the job done quickly. So conductance adds in parallel, resistance adds in series. If you are looking through some kinds of review books, or if you've taken this in a different context or anything like that, you might have seen for a parallel arrangement something that looks like this. 1 over R total equals 1 over R1 plus 1 over R2 plus, or even and R total equals 1 over R1, 1 over R2, all to the power of -1. These mean the same thing. This thing is just G1, this thing is just G2, this thing would be G total. And over here where I've got this to the power of -1, what I'm saying is I've got 1 over R1 plus 1 over R2 plus ... 1 over that equals R total, which if I solve that back out, I can multiply, I can divide, and I'm going to get the exact same equation that I had up here. They all mean the same thing. I like to think of this in terms of conductance because conductance is easy to find and it's easier to remember, I think. Here is the quantity that adds directly in the one case, here's the quantity that adds directly in the other, versus remembering a formula that starts with the 1 over or that has a bunch of fractions. I would rather remember myself the direct kind of addition formula. They both work just fine.